As a preface, before I start the CBA, I wanted to find a topic that was suitable for not only CBA 1 in engineering but also CBA 1 in technology, with a good bit of overlap that can be used in an exemplar in a classroom. I also wanted to design a CBA that could also be used as a teaching resource, and I feel 3D printing is not currently covered in good enough detail, and with it being such an emerging and important technology, we should be able to teach it to a high standard to our students, and I feel this resource could be quite helpful in doing that.
To convey this CBA, I'm using a mix of different resources. These include images, text, GIFs, voice notes, and link videos, and these will give a more holistic view of the use of 3D printers. To research the CBA on 3D printing, I've broken into two sections, with primary research being one of the operations of 3D printers and the experiment. I used 3D printers and explored their use to inform me for the operations section, and I conducted an experiment on infill for that section. For secondary research, I first used the strands and elements to identify which areas I wanted to investigate, and this led me to material properties and the types of 3D printers. I was able to explore these in more detail, which fed into my conclusion and eventually my evaluation.
When looking at the statements of learning, I could link these to my CBA in the following ways. Statement of Learning 19 is related to 3D printing as a technology that has come leaps and bounds in the last 2 decades. It went from an emerging technology to one widely available that has so many uses such as rapid prototyping and reduced waste in manufacturing fields like healthcare and aeronautics. Statement of Learning 20 also relates with 3D printing allowing rapid iterative development and prototyping. 3D printing can allow the production of complex parts and tools without the tooling required of traditional manufacturing processes. Statement of Learning 21 is also related to 3D printing, as 3D printing can develop models and products using a wide range of materials including plastics, metals and ceramics. There are several different types of 3D printing, with the main ones being fused deposition modeling or FDM, stereolithography (SLA), and selective laser sintering printing (SLS) printing. Statement Learning 23 is also related, with 3D printing is related to SOL 23 by allowing us to bring our designs to realization by quickly iterating on our designs and refining our designs. 3D printing allows physical testing and evolution of design ideas without the product waste associated with traditional manufacturing processes or the tooling that's also required, which can be quite intensive on materials.
I have selected a number of strands to inform my exploration of 3D printers within the engineering subject. So the principles of engineering that I hope to explore throughout the CBA are additive manufacturing, machine design, this is the types of 3D printers, CAD and slicing, so this is the use of SolidWorks and then slicer software such as Cura and Prusa, material science, so the differences in materials such as ABS and PLA and how their properties affect each one, and also the quality control. I want to explore how it can go wrong.
With this CBA, I'm going to focus on 3 main types of 3D printing. These are fusion deposition modeling or FDM printing, stereolithography (SLA) printing, or selective laser sintering (SLS) printing. These are the most common or readily available types of printing. While some are more expensive than others and they each have their own benefits and cons, these are the main ones we would focus on. FDM printers are by far the most common type of printers, and these can be quite cost effective and quite easy to use. Now, they are still complicated and complex machines, but generally speaking, they're the most cost effective, and they can probably do the most variety of parts, while they can create both functional and aesthetic pieces. Their common brands would include the likes of Creality, Ender and Prusa. When we look at the types of FDM printers, Generally speaking, they're Cartesian and delta, but sometimes we can find polar and robot arm printers. Cartesian printers are often the most cost-effective printers and seen in products such as anycubic printers, Creality printers, and Prusa printers. Delta printers are slightly less common, but they are quite good for creating taller objects with higher accuracy. From my primary and secondary research, I was able to deduce that the most common types of 3D printers are Ultimaker, Prusa, MakerBot, Creality, and iCubic. Oftentimes we'd see Ultimaker and MakerBot being used in classrooms along with Dremel printers, and anycubic Creality and sometimes Prusa are quite popular with hobbyists and prosumer markets. These aren't as common in classrooms due to the fact they don't have enclosed setups as seen in the Dremel or Ultimaker as shown in these images. From my primary research, particularly from exploring them in the 3D printing room, I was able to see that SLA printers are more useful for creating static objects with very detailed and sometimes complex faces. These such as like characters or sometimes even gears. They wouldn't be as strong as the filament or FDM printers.
In order to create a 3D print, we must first design the part or model we want to create in a 3D modeling software. Personally, I use SolidWorks, and this is why I've shown here my part file, and then I've converted it to an STL. The STL can then be used in a slicing software. There are two types of slicing software I generally use. These would include Prusa Slicer and Cura. They are the main 3D printing slicers available on the market, and these work quite well with both Prusa printers, anycubic, Ultimaker, and a variety of other printer brands. 3D printing can be quite an effective tool when prototyping parts, and they can influence the design. Previously, when we were creating models in CAD, we wouldn't have been able to create them in person in an easy way as we can with 3D printers. We can also see the part before it goes to final manufacture using more traditional manufacturing methods. The variety of materials we use in 3D printing. When FDM printing, we mainly use polymers, and a lot of the time these polymers are thermoplastics. The most common materials we'd use would be PLA, ABS, and nylon, and the most common and most widely used would be PLA. PLA is a renewable resource, and in the correct circumstances is fully recyclable. The different types of materials would have different characteristics and how they behave. This is a decision we have to make before printing, as we want to have different characteristics for the prints. Infill is quite an important thing we need to decide on before we print the part. This is done in the slicing software. The infill can vary from 0% to 100%, and the different percentage infill can affect the characteristics of the 3D print. This is something I want to explore with the CBA. The first experiment I conducted on infill was with mass. I printed two different parts, the exact same dimensions as test pieces. One had 5% infill, which was 1.8 grams. The other had 25% infill, which was 1.98 grams. This characteristic of mass can be quite useful for us, as sometimes we need a lighter part, and sometimes we may need a heavier part if we need a certain weight minimum, and this can affect our design solution. The second experiment I conducted was on the strength and flexibility of these parts. I took the two previous specimens with 5% infill and 25% infill. I tried to break them in the same way a stress strain test would in a laboratory. Fortunately, I don't have access to that machinery, so I snapped them in half, or attempted to. The 5% infill snapped in half, while the 25% only partially snapped, with half the material, or half the specimen still being attached. This showed that how the different percentage infill affects the flexibility and the strength of the part, and in this case, the 25% infill won. This is a quite important characteristic to keep in mind when 3D printing and designing for 3D prints, and also in our design solutions. Oftentimes 3D printing can go wrong. It's quite a complex series of operations to create a part, and things that could cause the 3D print to go wrong could include incorrect temperature settings, so this is in the bed and in the nozzle, bad bed adhesion, so this can be due to not having a high enough bed temperature. It also could be things like dust is on the build plate, or other issues such as gunk on the plate or other things of that nature. Mechanical issues could also be if some of our parts fail, such as our nozzle, our heating elements, our stepper motors, etc. We could also have model design issues. So when we create the part in CAD, we can pretty much do anything in CAD, but that may not be creatable with a 3D print part. So this is something we have to bear in mind. We could also have software issues, so sometimes we're relying on the software to create the part. This might not always be right. We could also have environmental issues. If you're trying to 3D print in a room that's too cold, the print might cool too quickly. It could also be an environment that has lots of humidity, and this would affect the 3D print material. And as such, the quality of the filament can vary. So some cheaper filaments may have a reliability range of 0.5 mil, whereas good 3D print would have, or print filament I should say, would have a reliability of 0.03 mil. And as such, you can see two photos here where I had 3D print parts fail on me, one more drastic than the other. From the CBA, I gained a lot more information about and knowledge surrounding the operations of 3D printers and the different types. I was able to learn more about FDM printers and how they operate and how they're the most common, as well as the infill, or the material I should say, and the types of material that we use and why we use certain materials for certain reasons. Also learn more about the way we design our parts to be printed, our models to be printed on 3D printers, and in particular how our design can impact the model overall. I also learned more about how the properties and the infill have a major impact on our final designed parts, especially when we consider how much infill to include, and we have to be cognizant of this when we design parts, as well as the weight and the impact that can have on our parts. And I also learned a lot more about the terminology associated with the 3D printing, but I would rather have gone into more detail on this and more detail in general about SLA and SLS printers, but there just wasn't the time for this. So when evaluating this CBA, I took it under a few different headings. From what went well, I made a good exploration of FDM 3D printers, and I used a variety of communication methods to do this, such as voice notes, images, and external videos, and I quite enjoyed exploring the use of infill. I also looked at the heading of what did I change from the feedback. So from the RM compare feedback, it was broadly surrounding that I didn't have enough primary research, so that's why I focused on the experiment I did. I also was said to have had a lot of text heavy, so I included more images and videos. I also needed to explore the relevance of the statements of learning to the CBA, and I tried to do that throughout. I also explored the heading of what didn't go well. I don't think the experiment was as in-depth as I would like. If I was to do it again, I'd probably explore more of the properties of the 3D print parts, as well as I would like to look into SLA printers as well, or SLS printers I should say, as this wasn't quite adequate. If I was to do it different, I'd probably focus on the different print materials as well as these properties, and also like to explore SLA and SLS printers into more detail.